The condensed phases. Intermolecular forces are attractive forces that hold particles together in the condensed phases. The magnitude and type of intermolecular forces is what determines whether the particles that make up a substance are a gas, a liquid, or a solid. If there are practically no intermolecular forces, you will have a gas. If you have relatively strong intermolecular forces, those particles will probably stick together and you will form a liquid, but they are still able to move around each other. Whilst if the forces are really strong, the particles cannot move at all and you end up with a solid. Properties of liquids. Surface tension. Surface tension is the amount of energy required to stretch or increase the surface of a liquid by a unit area. The stronger the intermolecular forces, the higher the surface tension. Capillary action is the movement of a liquid up a narrow tube. Two types of forces bring about capillary action. Cohesion is the attraction between like molecules, and adhesion is the attraction between unlike molecules. Examples of these effects can be seen in these two images below. On the left, we have water in a graduated cylinder. When adhesive forces are greater than cohesive forces, the liquid is most likely to be attracted to the material around it as opposed to the liquid itself. So if we look at the meniscus, the top of the water in the graduated cylinder, we will notice that it is curved up towards the glass because the water is more attracted to the glass than it is to itself, the water. So it curves up because it wants to be more in contact with the glass. On the right, when cohesive forces are greater than adhesive forces, we see the opposite effect. We see a bulge of the material being attracted to itself and less attracted to the glass around it. This example here is mercury. Viscosity. Viscosity is a measure of a fluid's resistance to flow, or in layman's terms, the thickness of it. The higher the viscosity, the more slowly a liquid flows. Liquids that have higher intermolecular forces have higher viscosities. Here in table 12.1, we have a list of the viscosities of some familiar liquids. For example, water has a viscosity of 1.01 times 10 to the negative 3, whilst blood has a viscosity of 4 times 10 to the negative 3. You know that blood is thicker than water. That's the saying. Well, it's true. It is more viscous also. Glycerol at the bottom here has a viscosity of 1.49. That's like, 1,000 times thicker than water? Crazy, right? Vapor pressure of liquids. Vapor pressure is a measure of the tendency of a material to change into its gas form. Vapor pressure is also dependent on intermolecular forces. If a molecule at the surface of a liquid has enough kinetic energy, it can escape to the gas phase in a process called vaporization. So examples here, at a low temperature, the number of molecules with enough kinetic energy to become a gas is usually relatively low, shown by the graph on the left. Whilst on the right, at a higher temperature, the number of molecules with enough kinetic energy to escape to become a gas increases, and therefore you would expect more vaporization. The vapor pressure increases until the rate of evaporation equals the rate of condensation. Evaporation is when liquid water turns into gas, and condensation is when gaseous water turns into liquid. When these two processes are occurring at the same rate, the system is in dynamic equilibrium. So what does it all mean? Well, here's an example. If we had this chunk of ice inside a beaker, shown on the left, inside a container that is sealed with a barometer made out of mercury to the right of it. At first, you would have a frozen liquid and empty space, and the pressure would remain relatively constant. Once the ice would start melting, some of those molecules of water are going to form gas or water vapor. This is going to increase the pressure inside the system, i.e., vapor pressure. This will continue to increase until you reach an equilibrium where you have equal amounts of evaporation as you have condensation. This is when your pressure will not change anymore and you have reached your maximum vapor pressure at that temperature. The vapor pressure increases until the rate of evaporation equals the rate of condensation. So in other words, the rate of evaporation remains constant until the rate of condensation reaches the same rate as evaporation to reach an equilibrium. Vapor pressure increases with temperature, as shown with these three liquids. The Clausius-Clapeyron equation relates the natural log of vapor pressure and the reciprocal of absolute temperature. Looks like this. The natural log of vapor pressure equals the negative molar heat of vaporization over the gas constant times temperature in Kelvin plus C, which is an experimentally determined constant. When we plot the natural log of the vapor pressure versus reciprocal temperature, you end up with a straight line with a slope of negative change in enthalpy of vaporization over the gas constant R. We assume that the change in enthalpy of vaporization is independent of temperature. This equation helps us calculate the enthalpy of vaporization, or it can help us calculate the temperature at different vapor pressures or the vapor pressure at different temperatures. It's a relatively versatile equation. It can also be rearranged into a two-point form to give you the natural log of pressure 1 over pressure 2 equals the enthalpy of vaporization over the gas constant times 1 over temperature 2 minus 1 over temperature 1. This equation allows us to calculate how much we need to change the temperature to reach to a different pressure, or what pressure would it be if we change the temperature a certain amount. Moving on. Boiling point is the temperature at which the vapor pressure equals the external atmospheric pressure. The boiling point varies with external pressure, and it varies with the magnitude of intermolecular forces, i.e., if you're at a higher pressure, your boiling point is going to be higher. If you're at a lower pressure, your boiling point is going to be lower. And if your molecules have strong intermolecular forces, then your boiling point is going to be higher. Properties of solids, the melting point. Melting point is the temperature at which the energies of the individual particles enable them to break free of their fixed positions, i.e., when are they able to start moving. The amount of energy required for this is directly related to the strength of the intermolecular forces between the molecules. The table below shows the elemental hydrides of pretty much all the elements in the main group of the periodic table. You will notice that the second period elements seem to all have higher melting points than the ones below. This trend is because of those strong intermolecular forces between the most electronegative atoms. You then see a dip in the melting point as these intermolecular forces are weakened. But as the elements become heavier as you go down the periods, you will find that the melting points start increasing again from the sheer size of the atoms. Here we have a table showing different substances, their molecular masses, the types of intermolecular forces they have, and their melting points. You will notice that the molecular masses do not really correspond to the melting points themselves. It is definitely the types of intermolecular forces that really matter. For example, helium, a gas that pretty much only has dispersion forces, has a really low melting point of negative 272.2. i.e. if you wanted to see a solid helium, you would have to freeze it to absolute zero. Water, on the other hand, has strong dipole-dipole moments and hydrogen bonding, and therefore its melting point is zero, that is 273 Kelvin. Then we have hydrogen fluoride, a molecule that is slightly heavier than water, which has a melting point of negative 83.6 because the hydrogen bonds are weaker than those in water. And then we have lithium fluoride, which has an ion-ion bond with a melting point of 845. It's a crazy difference. So as we work down here, you will notice that the ion-ion interactions are always going to give you a very high melting point, whilst hydrogen bonding is also going to increase your melting point substantially compared with molecules of the same size. Vapor pressures of solids. The vapor pressures of solids typically are very low at room temperature. However, a few exceptions are shown below. The one on the left is mothballs. It's naphthalene. You will probably recognize it as a very smelly solid. Usually, if you can smell the solid, it has a high vapor pressure. The pink thing in the middle is iodine, elemental iodine even. It looks like a gray solid, but if you leave it in a container, it will usually form a purple gas because of the iodine forming a gas. So once again, it has a high vapor pressure. And then finally, dry ice. If you put it into a sealed container, that sealed container will explode. So here we have an empty bottle and a bottle with dry ice. You're noticing that the bottle is already bulging. This has a very high vapor pressure. Amorphous solids and crystalline solids. So it turns out there are multiple different types of solid. A non-crystalline amorphous solid is probably going to have an irregular pattern of its components, such as the stuff on the left. This is non-crystalline quartz glass. Whilst crystalline solids are going to have a very almost perfect regular structure between its atoms. They are all laid out in a very repetitive manner, like the example on the right, crystalline quartz. Amorphous solids lack a regular three-dimensional arrangement of atoms. Glass, for example, is an amorphous solid and a fusion product. Of course, not all glasses are equal. You can have different levels of mixtures, so to speak. If you have pure quartz glass, which is 100% silicon dioxide, it's going to be the most crystalline of the amorphous solids. It has low thermal expansion, it is transparent to a wide range of wavelengths, and it is used in optical research due to its somewhat perfect state. Pyrex glass, on the other hand, has up to 25% of borax impurities with maybe some aluminum oxide in it. It has a low thermal expansion, but is transparent to visible and infrared light, but not to ultraviolet light. This is used in cookware and laboratory glassware due to its resistance to heating, so it doesn't crack under heat. And then finally, soda lime glass, which is 75% silicon dioxide, 15% sodium oxide, and 10% calcium oxide, is actually very reactive to chemicals and can crack when you heat it and then cool it quickly. However, it transmits visible light but absorbs UV light and is most often used in windows and bottles. All of them are amorphous solids that don't follow a perfect crystalline pattern, but you could expect that the most amorphous is going to be the least stable. A crystalline solid possesses rigid and long-range order. Its atoms, molecules, or ions occupy specific positions. A unit cell is the basic repeating structural unit of a crystal solid. So if you look at the crystal, you break it down to the smallest possible unit that repeats itself, that will be your unit cell. Just note that the unit cell is not necessarily just one single atom. It will be a cluster of atoms that repeats itself. There are 7 types of unit cell. You have the simple cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. The shape of the unit cell pretty much translates to the shape that you would expect the crystal to form on a macro scale, i.e. the size that you would be looking at. So for example, sodium chloride has a simple cubic unit cell, and therefore when it forms its crystals, they tend to be cubic. The coordination number is defined as the number of atoms surrounding an atom in a crystal lattice. The value of the coordination number indicates how tightly the atoms are packed together. So the bigger the coordination number, the more tightly packed they are. The basic repeating unit in the array of atoms is called a simple cubic cell. There are three types of cubic cells. You have the primitive cubic, which is just an atom on every corner of the cube. There's the body-centered cubic, which is an atom on every corner of the cube plus an atom in the center of the cube. And then you have face-centered cubic, where you have an atom at every corner of the cube and on every face of the cube. As you can tell by these cubic cells, you would expect the face-centered cubic to have the most atoms or the highest coordination number, whilst the primitive cubic should have the least atoms or the lowest coordination number. In a body-centered cubic cell, shown BCC, the spheres in each layer rest in the depressions between spheres in the previous layer. The coordination number is 8. Think of it as if you were to stack eggs. You would have one layer of eggs, and the next layer of eggs would probably go in between the bottom layer of eggs, just so that it's more sturdy. This would be body-centered cubic. In a face-centered cubic cell, shown to FCC, the coordination number is 12. So with eggs, instead of resting the egg on 3 lower eggs, you would be putting the egg just resting on 2 other eggs. This way you fit more eggs in between the other eggs. These unit cells are cubic though, and you will notice that if we have an atom on the corner, a lot of the atom sticks out from the cube. So we have to solve this. Most of the atoms in the cells are shared by neighboring cells. A corner atom is shared by 8 unit cells. An edge atom is shared by 4 unit cells, and a face-centered atom is shared by 2 unit cells. So, say a primitive cubic cell. So for example, a body-centered cubic structure has 8 atoms around it, or 1 atom on each corner, but in fact the unit cell that continues only has an eighth of an atom on each corner, because it's not like you can stack these cubes with full atoms. You would have to have an eighth of an atom, and when you put 2 together you end up with a quarter of an atom. You put another 2 to that, you'd have a half an atom, and then you stack them into a cube and you'd end up with 1 full atom on each corner. Long story short, it will look something like this. A simple cubic cell has the equivalent of only 1 complete atom contained within its cells. There are 8 atoms at the corners, so 1/8 times 8 will give you 1 equivalent atom. Now we have a truly repeating unit. If we start stacking these cubes together, we will start getting a repetitive structure that follows a simple cubic cell as a unit cell. A body-centered cubic cell has 2 equivalent atoms, the 1 full atom in the center and the 8 corner atoms giving you 1 equivalent atom. So we end up with 2 atoms. A face-centered cubic cell contains 4 complete atoms. There are 8 atoms at the corners, which are 1/8 in size, so that would give you 1 equivalent atom, and then 6 atoms on the faces, each of which is half an atom. So you end up with 3 equivalent atoms from the faces to give you a total of 4 equivalent atoms overall. This is a very efficient way of stacking spheres. A different type of packing is the hexagonal close-packed structure, or HCP structure. Here, the packing starts with a layer of atoms in which a second layer is fitted into the depressions of the first layer. The third layer then gets placed directly on top of the first layer, so that you end up with an ABA structure. This is a hexagonal close-packed structure. For a cubic closed-packed structure, or a CCP structure, you initially get the same type of layering with the second layer fitting into the gaps of the first layer, but then the third layer now does not sit directly above the first layer, so you end up with an ABC type layer. Note that from the top down view, you will notice that there is a gap straight down the middle for a CCP, but no gap for an HCP structure. Both of these systems achieve the highest packing efficiency of spheres. The hexagonal close packing has an AB-AB layer, and the cubic close packing actually corresponds to face-centered cubic cells, so as we know, it's relatively high efficiency. But this stacking is an ABC-ABC type packing. But intersection of the unit cell is at an angle from this layering. What if we wanted to figure out the size of the unit cell? Well, the edge length of the unit cell, A, and the radius of the atoms involved in this packing, R, are related. So for a simple cubic unit cell, the edge length is equal to 2 times the radius. For a body-centered cubic, the edge length is equal to 4 times the radius divided by the square root of 3. This can be derived using Pythagoras' theorem on the cube. And the face-centered cubic has the edge length equal the square root of 8 times the radius, which can also be derived from pretty much Pythagoras' theorem. You are not expected to be able to derive these, but you are expected to be able to use the equation to figure out the edge lengths of a unit cell. Types of crystalline solids. Ionic crystals. Ionic crystals are composed of charged ions that are held together by Coulombic attractions. So for example, sodium chloride has sodium ions and chloride ions. The unit cell of an ionic compound can be defined by either the position of the anions or the position of the cations. So for example, the structure on the left has a face-centered cubic structure with respect to the chloride anions, with the sodium ions filling in. Whilst on the right, we have a face-centered cubic structure of the sodium ions with the chloride ions filling in. Here are 3 crystal structures of ionic compounds. We have cesium chloride, which is just a simple cubic lattice. We have a zinc sulfide or zinc blende structure, which is based on the face-centered cubic. And we have calcium fluoride or fluoride structure based on the face-centered cubic structure. Note that in the first one, cesium chloride, the simple cubic lattice is focusing on the chlorides. With the zinc blende, we are focusing on the sulfides, and with calcium fluoride, we're focusing on the fluorides. Covalent crystals. In covalent crystals, atoms are held together in an extensive 3-dimensional network entirely by covalent bonds. Examples here include diamond on the left and graphite on the right, both having very distinct crystal packing. In molecular crystals, the lattice points are occupied by molecules. The attractive forces between them are van der Waals forces and/or hydrogen bonding. So for example, in water, the molecules are held together by hydrogen bonding, giving you this relatively repetitive lattice structure in ice. Note that the units are not single atoms, they are the actual molecules of water. In metallic crystals, every lattice point is occupied by an atom of the same metal. The electrons are delocalized over the entire crystal. Therefore, delocalized electrons make metals good conductors. Large cohesive forces resulting from the delocalizations make metals strong. Sharing is caring. Here's a nice summary of the types of crystals and their general properties. So ionic crystals are attracted pretty much by their charges and tend to be hard, brittle, with very high melting points and poor conductors of heat and electricity. Covalent crystals have covalent bonding and are also hard, brittle, with high melting points and poor conductors of heat and electricity. Molecular crystals tend to only have dipole-dipole forces or hydrogen bonds holding them together and end up being soft with low melting points but still being poor conductors of heat and electricity. And finally, metallic crystals have metallic bonds with variable hardness and melting point and are good conductors of heat and electricity. Moving on. Phase changes. A phase is a homogeneous part of a system that is separated from the rest of the system by a well-defined boundary. When a substance goes from one phase to another phase, it has undergone a phase change. Here are some examples of phase changes. When water freezes, when it turns from liquid to a solid. Evaporation of water, where the liquid turns into a gas. The fusion of ice, or the melting, when a solid turns into the liquid. The condensation of water vapor, when water gas forms water liquid. And sublimation of dry ice, where solid carbon dioxide spontaneously turns into gaseous carbon dioxide. There are 6 possible phase changes. Learn them all. We have melting or fusion, solid to liquid, vaporization, liquid to gas, and sublimation, solid to gas. We then have the opposites, deposition, gas to solid, condensation, gas to liquid, and freezing, liquid to solid. You need to learn these terms so that you are not caught off guard when someone starts talking about these phase changes. The boiling point of a substance is defined as the temperature at which its vapor pressure equals the external atmospheric pressure. The molar heat of vaporization is the amount of heat required to vaporize a mole of substance at its boiling point. In the table below, you will notice that there is a pretty good relationship between the boiling point and the enthalpy of vaporization. The bigger the enthalpy of vaporization, the higher the boiling point, with some exceptions. The critical temperature of a substance is defined as the temperature above which its gas cannot be liquefied. The critical pressure is the minimum pressure that must be applied to liquefy a substance at its critical temperature. These are values specific to molecules, and you will probably have to look them up if you require them. The transformation of a liquid to a solid is called freezing. The reverse process is called melting or fusion. The melting point of a solid or the freezing point of a liquid is the temperature at which the solid and liquid phases coexist in equilibrium. In dynamic equilibrium, the forward and reverse processes are occurring at the same time. So when you have a cube of ice in water, the water is freezing around the ice and the ice is melting into water. This is usually a dynamic equilibrium skewed towards the water, and hence as time goes on, the ice will melt away into water. Something interesting happens when we look at the heating curve though. At the point of melting, the solid and the liquid are in equilibrium and the temperature remains constant until all the solid has been melted, at which point the liquid will increase in temperature until it reaches the boiling point, at which point the temperature will remain constant as the liquid and vapor are in equilibrium. After that, you will be able to then increase the temperature of only the vapor. If you think about it, this makes sense. If we start boiling water, the temperature remains at around 100 in the liquid, and we can only get hotter than 100 if we heat vapor and not the water. The molar heat of fusion is the energy required to melt 1 mole of a solid. Note that the enthalpy of fusion is independent of the actual temperature of the melting point. It really depends on those intermolecular forces of your compound. Sublimation is the process by which molecules go directly from solid phase to the vapor phase. Deposition is the reverse process of sublimation. The molar enthalpy of sublimation of a substance is the energy required to sublime 1 mole of a solid, where the enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. For example, here we have solid iodine in equilibrium with its vapor, the purple gas. As iodine sublimes, we can measure the energy or the molar enthalpy of sublimation, and for example, we could figure out the enthalpy of vaporization from a different condition. This would allow us to calculate the enthalpy of fusion without ever actually measuring it directly. Phase diagrams. A phase diagram summarizes the conditions at which a substance exists as a solid, liquid, or a gas. Pictured here. The triple point is the only combination of pressure and temperature where the 3 phases of a substance exist in equilibrium. This phase diagram here is for carbon dioxide. You will notice that at most temperatures it seems to be a vapor, which makes sense. Carbon dioxide is a gas at 1 pressure. But if we increase the pressure at lower temperatures, we are very likely to be able to make solid carbon dioxide. At warmer temperatures, it's unlikely we will be able to make solid carbon dioxide even at higher pressures, but we may be able to make liquid carbon dioxide. The triple point, where all the phases meet, happens to be at pressure of 5.2 atmospheres at negative 57 degrees Celsius. Every substance has a different looking phase diagram. Here is the phase diagram of water. You will notice that at 0 degrees Celsius and 1 atmosphere, we have a phase between solid and liquid, which makes sense. That is when your water would melt. If we look at 100 degrees Celsius at 1 atmosphere, we see the phase change of liquid and vapor. You'll notice at 1 atmosphere, water remains a solid or a liquid until above 100 degrees Celsius. The triple point happens to be at 0.0 degrees Celsius and 0.006 atmospheres. Learn how to read phase diagrams, and that this way you will always be able to figure out at what state you would expect your material at specific temperatures and pressures.